The second type of reaction that we encounter in aqueous solution is an acid-base reaction. Acid-base reactions are a category of reactions where we have what's called proton transfer happening in solution. To really understand what's going on, we need to define what acids and bases are. And there are two definitions that are going to serve us this semester: the Arrhenius definition and the Bronsted-Lowry definition. Let's look at the Arrhenius definition first. The Arrhenius definition of acids and bases tells us that an acid is a species that produces a certain type of ion in solution. And the type of ion that we're talking about are H plus ions. H plus ions, if you think about them, okay, if we look at hydrogen, it has the atomic number 1, the atomic mass is 1. If we have a positive charge, that means when we're talking about the H plus ion, really all it is a proton. Because hydrogen, neutral hydrogen by itself would just be a proton and an electron, no neutron, because 1 minus 1 is 0, no neutrons. So if neutral hydrogen is just a proton and an electron, the H plus ion has lost the electron. So we simply just have a proton. So the Arrhenius definition of an acid is that it's a species that produces protons in solution. So H plus ions and protons are synonymous. Arrhenius holds that a base produces hydroxide ions in solution. So OH minus ions are also known as hydroxides. And a base is going to be a species that produces OH minus ions in aqueous solution. The Bronsted-Lowry definition, though, is also a bit broader and maybe more useful. The Bronsted-Lowry definition holds that an acid is a proton donor and a base is a proton acceptor. So when we look at an acid-base reaction, the acid is going to be the species that gives up its proton. The base is going to be the species that accepts the proton. So let's put these ideas into practice by writing molecular ionic and net ionic equations for the reaction of an acid, nitric acid, with potassium hydroxide in aqueous solution. So again, we are translating these words into a chemical equation. Let's start by writing the molecular equation for this. Nitric acid is HNO3. Okay, that's one of the ones that you may have memorized from the previous chapter when we talked about nomenclature of various ionic compounds. This is all in aqueous solution, so I'm going to write everything as an aqueous species. Potassium hydroxide has potassium and hydroxide in a 1-to-1 relationship because they each have a charge. K is K plus and OH is OH minus, so they come together in a 1-to-1 relationship. Whenever an acid and a base react together, the acid serves as the proton donor and the base as the proton acceptor. So what happens here is the hydroxide, OH minus, accepts a proton to become water. So water is always going to be a product of a reaction between an acid and a base like this. The KNO3, I'm just going to write them as kind of spectator ions that are not really involved in the reaction. So water can't be aqueous. Water is a liquid. Water is the solvent, and it can't be a solvated in itself. So I'm writing it as an L, a non-aqueous species. Is this reaction balanced? Well, it looks like it's balanced as written. If I had written down calcium hydroxide, for instance, I would have to balance it. So this is the molecular equation. Now, let's write the ionic equation where we separate out the species into ions. So the definition of a strong acid is a species that completely dissociates into ions. So nitric acid is really H plus NO3 minus completely separated in aqueous solution. Same with the strong base. The strong base is completely separated into its component ions in solution. So the left side of the equation, the reactants, look like that when I pull apart the species into their component ions. Water is water. That's just a liquid. It can't be pulled apart into ions. But the potassium and the nitrate are ionic species that I could write separately like this. So here's the total ionic equation for that acid-base reaction. And you will notice that certain species are the same on both sides of the reaction. So that means that when I write the net ionic equation, I can cancel out species that are spectator ions. So potassium, for example, is the same on both sides of the chemical equation. It's a spectator ion that doesn't change over the course of the reaction. Nitrate as well is a spectator ion. It doesn't change over the course of the reaction. So the net ionic equation boils down to H plus OH minus, giving liquid water. This, you will notice, is protons plus hydroxide making liquid water. And in fact, you will find that this net equation holds for any acid-base reaction that we're going to see this semester. What is this called? Well, effectively here we have acid combining with base to make water. This is neutralization. Okay, acid plus base making neutral water. So this net ionic equation for neutralization is expressing the idea that the H plus ions react completely with the OH minus ions and vice versa in the solution. Okay, to make nothing but water. So you will find as you're doing these kinds of problems that all of the acid-base reactions that you're going to be writing boil down to the same net equation, net ionic equation. So this equation where H plus OH minus come together to make liquid water, that neutralization equation is going to apply for every acid-base reaction that you see this semester.